Hey everyone, today is day 63 of my Coding Everyday challenge. So recently I've been doing 2D dynamic programming questions and I felt not great with them, so I'm going to go back and do some easier problems. I also have to film tomorrow's video today, so this will probably be a short video. Maybe I could try like just a sliding window problem, I guess. So we'll try minimum size subarray sum. Have I tried this one before? No. Also, it's on LeetCode. All right, that's fine. All right, so let's take a look here. It's been so long since I've done problems like this because I've just been doing backtracking and dynamic programming and graphs and heaps and stuff. So I'm interested to see how I do on a more sort of classic problem. Right, so let's get started. So minimum size subarray sum. Given an array of positive integers nums and a positive integer target, return the minimal length of a subarray whose sum is greater than or equal to target. If there is no such subarray, return 0 instead. Okay. Okay, so we want the minimum length. The minimum length. So a couple things that come to mind. So first, I'm also going to try to stop using paint because in interview settings, you kind of just have to type it out here because I have gotten really used to using paint to explain my thought process, but that doesn't really translate perfectly with interviews and stuff. So I'm just going to try to kind of block out my thought process on a word editor or code editor here. So the first thing that comes to mind, and maybe I shouldn't jump into this so quick, but I'm thinking what we could do is, let me think for a second. So I'm thinking our window probably wants to get smaller. I mean, I guess a trivial solution to this would be, and what if there are, okay, we return the minimum length. Okay, so a trivial solution to this that I can think of is we would loop over everything with a window size of 1, and then we say, is the window just containing 2 bigger than 7? No. What about 3? What about 1? What about 2? And if none of those are true, actually, so if one of those is true, then we'll return 1 as our answer. Then we'll do a sliding window of size 2. So we'll sum together 2 and 3, and if that's bigger than 7, then we'll return 7. We'll return 2, and we'll just keep sliding, and we repeat this method until eventually the window size is the entire array. So that would be a trivial way of doing it. But that it feels like there could be a better way to do it. Another thought I had is you could start with the whole window. So you could start with everything as the window. And you would say, okay, is the sum of all of these numbers bigger than the target? And if it is, then we can shrink our window and keep checking. So maybe we would get rid of, let's say, the smaller element. So we'd get rid of 2, and then we'd check this and say, is this window still sum up to the target? And if it does, now we have a tie, so we can remove 3 or 3. So if we picked this one, so I'm seeing that this wouldn't work because, well, maybe it would, but in the case of a tie, it may not. Like if this, well, if this was a 4, if this right here was a 4, then we would get rid of this 3 and have this as the window. But of course the window here is 2. I mean, another thought I've had is instead of going from 0 to n window size in like 0, 1, 2, 3, 4, you could like binary search the window size. So you could start with a window size of half of n, and then depending on whether or not your target is bigger or smaller, you can adjust the window. So if you didn't quite reach your target, you could try going to the next halfway point window size. So that would be, so I could say binary search window size, and that would be log n. We do log n windows, and each window would be O of n. So that would be n log n. I think we could probably do better. Okay, so there's a linear and then there's n log n. So that's one solution. So how could we make it linear? Well, I'm wondering if we could so we have to do something with our window. I mean, could we sort it? No, that would be n log n. So we cannot sort it. What if we because normally if this problem was in, well, I was thinking normally sometimes what you do is grow your window, but here it's almost like we want to shrink the window. That's like what my gut is saying. Like we want to start with a big window and then shrink it until we can no longer shrink it. So we'd probably either want to start with a window size of the full thing or a window size of 1. Maybe we could even keep like a sum, like a 2D sum or something. So if we have 2, 3, 1, 2, 4, 3, we could say at this point, and then I guess we could have our window sizes or something like this. Okay, so then for all of them, no matter what our window size is, when we're just at this point, all right, does that work? I'll just do it like this. Okay, whatever. So when we're at this, regardless of our window size, our sum is 2. When we move to this, if our window size is 1, we would subtract our previous one and add 3, so it would become 3. With size 2, our window size would be 5. This would be 5, 5, and 5. With this one, so if our window is 1, it would be 1. And then here would be, so this is still n times, this is still n squared, but I think it may be a useful way of looking at it. Here our window size would be actually 4, would be these two. 3 would be the sum, and this would be the sum and the sum. Here would be 2. This would be 3. Window size here would be, yeah, so this seems like I'm just doing the quadratic solution, but like all at once, because for every number, we have to look at every window size. Maybe there's a better way that we can think of it. So maybe we could go until we encounter target. So we can keep expanding our window until we encounter target. So this would be, so it would keep like a running sum. Yeah. So it would be like 2, 5, 6, 8. So at this point, we know that this window has 7 in it. Then what we could do is check if this is bigger. Okay, so if this is bigger than that, we know we should move the window over. So there exists 7 in this window. We know if this is bigger or equal to that, there must also exist 7 in this window. So then we could change it to be, now our sum here would be 7, 9, 10. So now our window sum would be 10. And then we could say, okay, these are the same. So let's try to shrink our window. So we would shrink this 3. And then, of course, we'd keep track of the smallest window so far, which would be 4. So we'd shrink this 3, and then that would give us 7. So then we'd say, okay, our sum is 7, and our smallest window so far is 3. So then let's shrink again and see if we still have 7. So we'd shrink here, and then we'd say, okay, we only have 6 now, so we have to expand. So we already explored everything on this side, so now maybe we could expand our window to the right, and then that would yield 9 with a window size of 3. And then, okay, we are greater than the target, so we should shrink our window. So let's shrink from the smaller side. And then we would get this, which is 7, and then we update our minimum. Okay, so that algorithm would be O of n. So what is exactly the algorithm? I kind of went through it. So step 1 is increase window until you get target. When you have target, sum greater than or equal to target, you want to decrease window. Now my question is, do we always decrease it from the left side, or do we decrease it from the smaller side? So what if, let's say, so here, right, that gave us 5, 7, 8. So this gave us 8. If this was a 1, let me make a new example here. So if this was a 1, okay, so if this was a 1 and we had 8 right here, so we'd record 4 as our min window size sum. Okay, so it would be 4 here, and then we would decrease our window size. Yeah. So in this case, it's 2 and 2. So I guess intuitively it would make sense. Yeah, so we should never decrease it from the right. The reason being, if we didn't need that number, we would have already found a window here. So because we added this number, we know that it is essential. So we removed from the left. So decrease window from left. We'll say while sum is greater than or equal to target, decrease window from left. So we'll decrease the window from the left like this. And then when it's no longer equal, we will shift the window over. So we'll shift the window over. Or would we expand the window? I think before I expanded the window. But my problem with that is if we've already found a window, let's say, well, we've already found one of size 4. So there's no point in looking for size 4 windows anymore. So we would shrink from the left and then continue with size 3. And then if we ever find something that's, okay, so I've refined the algorithm a little bit. So we're going to keep going until we get target. So in this example, we get target here with a window size of 4 and a sum of 2 plus 2 plus 3 plus 1, which is 8. So we have a window of size 4 here with a sum of 8. Then, according to our algorithm, we'll shrink the window from the left, calculate the sum. So now the sum is 6, which is less than target. So this exits. So now we will continue scanning. So we'll move our window, and then we'll get 7 here. So our new min window is 3. So in that case, we would shrink from the left here, I guess. So because we're here, we'll shrink from the left here, and then we'll scan for 2s. And then we find this, 7 with window 2, and then we would shrink from the left and see that there's nothing. Okay, yeah, it looks good. Otherwise, continue sliding window. All right, looks good. And this should be O of n because we just have a window that goes through it. The right pointer of the window never goes backwards, and the left one only goes forwards as well. Okay, so that should work. So that looks good. And we'll say that this is O of n. All right, so we'll start by, I'll have a variable called total, which is 0. We also are probably going to want our left pointer and right pointers, which I'll set both of them. I guess I could set left to 0 and R to 1. Okay, now we'll say while R is less than length of nums. So we should keep increasing. Okay, and then we want to say while total is less than, or I guess greater than or equal to target, we should decrease from the left. So let's say L, I guess L plus equals 1 in this case. And then total, of course, so total would get decremented by nums of L, because that will be our stop condition eventually. this will be false. We need it to be false, and that's because we will decrement total. Okay. So we do this. Otherwise, we continue the sliding window. We also wanted to note that our minimum, so I'll say our result, is equal to, and then what do we return? If it's not possible, we return 0. Let me try it like this. So our result will be 0, and then here, result will be r minus L. So for instance, in this case, r would be, I think it might be +1 here. So r would be 3, L would be 0, so 3 minus 0 plus 1, that would give us our window size. Okay, every time we increase r, we want to say total plus equals nums of r. Okay. I think this might be it. Well, not necessarily. So, maybe. Okay, let's walk through an example with this algorithm. Okay, so I'll copy this up here. Okay, so initially we have L and R at 0, total 0, and result equals 0. So everything equals 0. While R is less than length of nums, that's true. Total will go up by nums of R. So total, I'll just keep track of the variables here. Total equals 2. Then L and R we'll just have in our head. And result, we'll also keep track of. Okay, while total is greater than or equal to target. So that is not true. 2 is not greater than or equal to 7. So R goes up by 1. We add 3 to total. Total is 5. This is still not true. R goes to 1. We add 6. This is still not true, so we add another 1. Now it goes to 8. So R is here and L is here. Total is greater than target. So result is going to equal to 3 minus 0 plus 1. This is our window size. Total will go, so now we want to shrink the window, so total will go down by 2, and L will go up to here. So now our window is like this. And then R will go up by 1. Okay, so that might be a slight error. So maybe L should go up by 2. So I'm thinking, so this was greater than, we decremented, we did the result, L goes up here to there, and then R goes to here. So our new window is this, but it should only be this. So maybe we could just undo the R change like this. So that way R would go up here and then jump back down. Well, I guess, so L would go up here, R would go back here, and then come back here with this one. And then our window would be like this. Okay, so at this point, total is 6. So now we'll increase R by 1. Well, in this case, maybe a more elegant way of doing it is we could add an if statement here and say if R minus L, or if R minus L plus 1 is greater than result, then L can go up. What I'm thinking there is, because for this, we don't really need to consider this one, right? Or we do. We should consider this. So with the code I have right now, I'm thinking, okay, so it's 4. L should come up. And then R goes up. And then this L would go up again. So that would kind of skip it. So maybe not. Okay, so we're at here. I'll just keep it like this for now. So we're at here. Or maybe I could say if R, or if total is less than, I almost want it to be like an else, like this. I mean, I could say continue here, so R doesn't go up by 1. It's the same thing. So that would make it, so we'd be here, total would go, so L would come up, and then we would just continue and not change R. Well, it would continue to this loop. I want it to go to this outer loop. Okay, whatever. I'll just do R minus equals 1. Okay, so then we'll be here. And then, yeah, so a problem I'm identifying is I got too caught up in the details of trying to make it perfect right there. So for interview settings, don't do that. Okay, 3, 1, 2. So this is our window. This is false, so R will go up by 1. Yeah, so this is the problem I was facing. So R goes up by 1. Now the total is bigger. Yeah, so I think what I want to say here is if R minus L plus 1 is greater than res. So in this case, we're here and then we increment R. Or do I not do that anymore? I might not have to do that anymore. Because we had L and R. R goes down by 1 and then comes back up by 1. Yeah. And then it'll check. Is that a redundant check? Because when we're here, so we shrink. Okay, so here is total is greater than target. We set the result to 4. We shrink it by 2. And then, so L goes up by 1. And then what's our expected behavior? We want it to, so it checks again. So maybe we actually do want it to just go here instead, because we actually do check this in this while loop. So I said earlier that we couldn't skip it, but that is L could go up. So R would go here, and then if R minus L plus 1, 4 is greater than res, if it's greater than or equal to res. Okay, I'll try submitting this or running this and see where that takes me. Okay, list index out of range. So we could say Okay, so it's the very first test case. So let me continue going through the test case. Another error, don't stop the test case midway. So I went into too much detail with the test case, and I got caught up in trying to perfect it too early. Okay, so we're here. For the millionth time, we're here. L goes up by 1 because total is greater than target. We decrement total to 6. And then R goes up by 1 here. And then we're checking, okay, this is equal to res, so we'll move L over. Okay, this is 7. So the result is 3 because this is true. So right now we're here. Okay, so total now will shrink the window, so total will go down by 1. And L is now here. And then we'll increase R. And then because this is bigger than the window size, we'll come here. And we say, okay, this is greater than or equal to target. So target will become 7. Result will become 2. Yeah, because it's 0, 1, 2, 3, 4, 5. So it's 5 minus 4 plus 1, which is 2. Now we shrink it to go to 3. Okay, so I don't really get why L is out of bounds. So I'm going to try running it again and logging what L is. And maybe I should have done that with R as well. So L is 3 and then 5 and then 6. So it starts at 0. And then the first time... Oh. Well, it's L is always moving up, which it shouldn't be. So... if this distance, it should be if it's less than or equal to, right? Or maybe I could just set L equal to R minus result. So if it's, like, let's say our result is 4, or let's say it's 3, right? Let's say we shrunk it here, and then it's 3. So then R goes up here. We want to automatically set it to index 2. So 4 minus 3 plus 1. So that'll always keep it at our window. Okay, same thing. So let's say R, how are we looking at? 33 minutes. Okay, it's been a while. So L is 4. So this feels off. Okay, so it starts at 0, 0. L goes to 2. Why is that happening? So L should not be going to 2. Yeah. So let me print inside inner loop. So this will tell us when it's registering that target is bigger. Okay, so that's just happening. So it's probably this. Maybe we should say it's the max of 0 and this so it doesn't go negative. Maybe it's going negative. Okay, let me print what this is. So this is 2, so that's messing it up. So R is 1 minus result, which is 0, plus 1. So how is that 2? Yeah. So it's this part that's throwing me off, basically, in the logic. It's like, how do we make L jump up to where it needs to go? So whenever we have a window and it's bigger, we just want to keep keep increasing L like this. And then after we're done, so when this is no longer true, so I might just need like an if-else statement here. So if it's not true, maybe. So let's say if total is less than target, then R goes up by 1. Like that, maybe. So we'd keep increasing R, and then when that's no longer true, we just decrease L until it's false. So in this example, it's true. So this is true. L goes here. It's false, and then it exits. And now R goes up by 1. Well, wouldn't it? Maybe this is also under the if statement? So maybe it's like this. Okay, so we'd get to this point. This would be false, which means this is true. So then it will keep repeating, and it could keep repeating, because if this is like 1,000, it should repeat until it goes to just 1,000. So we do need a while. Okay, L is going to go up by 1. Now it stops being true. Okay, so it stops being true. Now this must be true now. So that's going to say total goes up by this. So that's not like my intended behavior. I don't think it breaks anything, because then it would just shrink it again. I think this one would work, but it's not my intended behavior. My output was 4. Yeah. Okay, it's giving me 4. So that doesn't seem to be it. Okay, what's going on now? All right. Okay, so now I'm going to do like a full trace again of the example. I feel like maybe it's just because it's late, but I feel like I definitely could have. I don't know. I feel like I should be able to get this. Okay, it might just be because it's late. All right, so we start here. So this is true. Total is less than target. So we'll say total, and we'll say results. And also, just for precision, I'll do L and R. Okay, so they start at 0. This is true. So total goes up by 2. And R goes up by 1. Result is still 0. Okay, so that was that loop. Then we continue and go here. So same thing, total is less than target, so total will go up by 3, R will go up by 1, and then we continue. Total is less than target, so we're going to increase it by 1 and 1 here as well. Continue. Now R is at 3, 0, 1, 2, 3, so we'll increase it to 8, and this will go to 4. Is that the problem? 0, 1, 2, 3. Because, okay, so maybe we don't want R to increase. Okay, so that's unexpected behavior. So when we find this, so R is 1 too big. So if we say if total is less than target, then only then do we want R to increase. So I'm not going to worry too much about how it looks. I'm just going to try to do the logic. So then R would stay at 3. So we'd have 0, 1, 2, 3. So R would be here, and that's intended design. And then while total is greater than target, result will be equal to 3 minus 1 plus, 3 minus 0 plus 1, which is 4. And then total will decrease by 2. And then L will go up by 1. So now 1, 2, 3, these are indices with a total of 6, and our result that we stored so far is 4. So this looks good. Okay, then we're going to go back up. This part is not true. So we're going to skip. Wait, no, this part has to be true. Yeah, this part is true. Total is less than 6 is less than 7. So we're going to increase it by 4. Wait, 0, 1, 2. No, that would not happen actually. So okay. So we're at 3, 1, 2. That's good. And now it's going to see that this is true, and it's going to add 2 to give us 8, which is not what we want at all. So I'm almost wondering, like, So I'm noticing a pattern about the problem. It's that we always just, traverse our window. So L and R always go up by 1, except when the case that it's 0. So I wonder if it's not just after every loop, we just increase both of them by 1, unless, so if L equals, if it doesn't equal 0. So the only case we don't want to increase L is if it's 0. And that has to be increased this way. So I wonder if it's just like something like this. Plus equal nums of R. So I wonder if it's something like this. So after every iteration, we'll increase both of them by 1, but we'll shrink the window if it's, if the total is bigger. So let's try tracing it like this. I didn't have to do that. All right. So it's going to be 0, 0. Total is 0, and result is 0. Okay, this looks more simple to me. Okay, so R, that's true. Total goes up by 2. This is false, so R will go up by 1. And L is 0, so we're not going to move it because it's still growing. Yeah. Okay. 45 minutes. I would have liked to solve this in like 20, but let's try to shoot for under an hour. Okay, so that's that. Total goes up by the array at index R, which is 5. This is not true. R goes up by 1. Okay, then we're going to add, so R is here, so we'll add that. R goes up by 1. And then R, so R just went up by 1. Total goes to 8. Now here's where it gets interesting. So we have all of that. So result will be R minus L plus 1. So that's 4. Total will subtract L. So 6. And then R will go up by 1 to 4. And L, now that it's not 0, sorry, I didn't include 1 here. That got included here. So R was 3, but now it goes up to 4, and now L is no longer 0, so it will become 2. 0, 1, 2, 3, 4. So this is our new window. So we went from here, this is bigger, this is not bigger, so we move the window here. So that's intended design. Okay, now total will go up by nums of R. So 0, 1, 2, 3, 4. So total will go up by 4, making it 10. I think here I also need to add this part. So when L goes up, we also have to decrease it from the window. So when we were here, so we did this, we did this. So at this point, this loop exits, R goes up by 1. L is not 0, so we're going to decrease 3 from our total. So our total would have been 6. So we decrease it to 3. So it's like this. We decrease 3, and now our window is like that. And now this makes more sense because we're going to add 4 to our total to make it 7. Perfect. So now this is 7. So this will be true now. The result will be 4 minus 2 plus 1, which is 3. Total, so it's right here. So total will get subtracted because our window, is 7. So it'll be subtracted by 1 to become 6. And L will go up to 3. So 0, 1, 2, 3, 4, like this. R will increase. L will increase and also subtract 2 from the total. Okay, now we'll add 3 to our total. Um, I didn't update these 2 pointers. So now they both went up by 1, 0, 1, 2, 3, 4, and 5. Okay, so let's see if we can out of bounds error over here. So, okay, so we're at this line, so we add 3 to our total, which is 7. This becomes true. So then result equals 5 minus 4 plus 1, which is 2. Total subtracts from 4. L goes up by 1. Now R goes up by 1. And L goes up by 1. So then we'd subtract 3. And then R is out of bounds, and then we'd return results. Okay, let's try running this. Also, in the case of this, right, so R would just keep growing until it goes out of bounds, and then it would never update results. In this test case, R would keep growing, and then at this point, this loop would activate. We would record 1 minus 0 plus 1, which is 2. We'd subtract 4 and increase L by 1. Wait, this might be a problem. So we increase L by 1. Oh, but then it's fine again because we check if this is still true, which it is. So then result. Okay, I have confidence. So we may have to specify here while L is less than, because in the case that well, let's say we have just, I don't know, just a 4. So we would increase our total to be 4, and then this would I don't know. I wonder why this one is getting. Okay, list index out of range. So let me print. Oh, it's this one here. Because this one the total should revert itself. So if this is the last element when you try to go up, so R goes up. Yeah, so if they're both out of bounds, I see. So if L does not equal 0 and L is less than the length of nums, then we increase it. Okay, so just a little edge case there. Let's see if there's any other edge examples. Okay, perfect. So we actually got a good solution. All right. So let me think about how that went. So that was 54 minutes. So that was a lot longer than I would have liked for a medium sliding window problem. I really liked how I talked it through at the beginning, and I was able to figure out the solution without using paints. And I just kind of did it with the code. I noticed that I got too caught up in the details too early, which is a bad habit of mine, so I'll continue to look out for that. I also think I was focused on the edge case for too long, of when the window grows. But if you think like if this is a really big array, The most important thing that I should consider is just the general case when the window is somewhere in the middle. I was almost making the edge case of when the window is growing. I was making it into the general case, but it's actually an edge case. So what I'm trying to say is I think I should develop and write the solution for, when it's in the middle of the case for the general case, and then think about the edge case second. Because I failed to realize that, growing the window at the beginning is actually sort of an edge case in this problem. So yeah, focus on the general cases and don't get too caught up in the details early. Another thing, I liked my problem solving, but I'm surprised it took me that long to code it. And I think it kind of just comes down to what I was saying with the general case versus edge case thing. So in my algorithm, focus when you develop algorithms, focus on the general case. Focus on the general case, and then build your edge cases around that. Okay, so I think this is the exact same code. Just to be sure, I'll submit it again. And yeah, perfect. It's really great, actually. Beats 95%. So I'm proud of that. And I feel like I made a really great algorithm. It seems like a good algorithm. I don't know if this is like a little clunky maybe, but yeah. Anyway, guys, so thank you very much for watching. Today was day 63, and I will see you guys tomorrow for day 64. Thank you.